Okay, good morning everybody. Welcome back to Math 115. So today we are going to talk about A.7 and 1.1. So 75-minute lecture. I'm hoping to power through a decent amount of material today. Three homeworks are due soon. A.4 is due today, and A.6 and A.7 are both going to be due on Monday. So a word on A.6, you're going to have to scroll like all the way to the bottom of the list of assignments in it to be able to see it, because I had to add it in because the other instructor didn't make an assignment for A.6, but I wanted to have one. It's pretty short. I just added like 10 questions basically or something like that. Shouldn't take you very long at all. So those two homeworks are due on Monday. So today we're going to finish A.7, which is what you're going to need to do that other homework. And our next assessment is going to be Quiz 2 on September 8th. That's 1 week from today, I think. Right? Yeah, it's 1 week from today. Okay, so that'll be the next quiz. And office hours for this week are done. I did office hours on Monday and Wednesday, but next week my office hours will be on Tuesday and Thursday in my office in LeConte 439. Okay, so that's the 4th floor of the LeConte Math Building. So if you don't know how to get there, email me and I'll send you directions. What else did I want to say? Just a reminder, if you wake up feeling sick, please do not come to class. Go get a COVID test and do not return to class until your COVID test comes back negative. I think that's the only other announcement that I wanted to have. Does anybody have an administrative question before we start in on material for today? All right, Chris is here. We mark you present. Okay, if no questions, then let's start on material by, let me just first remind us what we talked about last time. Okay, so last time we started talking about equations. So up until yesterday, we were always talking about expressions, but not equations. Okay, so now we went from just general expressions involving x to now we're going to have an equal sign and we're going to put something on both sides of it. And this is where this kind of equation balancing comes in. So the tricky things about equations is that, well, tricky or nice, depending on your perspective, is that you actually can change one of the sides as long as you change the other side in the same way. Okay, so for example, I could add something like 7 on both sides of an equation, and it still stays equal to one another. I could also multiply both sides by a number. Of course, if I multiply by a number, I need to make sure I multiply the entirety of that side by that number. Okay, so we learned about a couple different equations, linear equations, quadratic equations. Those should have been pretty familiar. Rational equations and equations with radicals, maybe not so much. So the trick with rational equations was to multiply everything by the least common denominator between all of these rational expressions. And then the trick with radicals was to isolate the square root or the nth root first and then square everything. So that way we can get rid of any and all roots that are in our equation. And the last one was the hardest, I think, which was quadratic in form. Okay, so these are quadratic equations. Well, actually, they're not quadratic equations. They may be quartic equations or something like that, where the first and second term and third term share this relationship of like a 2-1-0 type of a situation, where what I mean by the 2-1-0 is that the power of the highest term is twice that of the power of the middle term, and the power of the last term is 0, okay? So if we have this kind of a relationship, then we can perform what's called a change of variables by letting u be equal to something like, as shown for this example, it was x squared, and then we rewrite the whole equation as u squared plus 2u plus 1 equals 0 instead of x to the fourth and x squared. Okay? So then we can go ahead and solve this one using factoring or the quadratic formula or whatever. And then what do we have to do? We're not quite done after we get the solution of the u problem, because then we have to reverse the change of variables that we did at the start. Okay, so we change the problem, and then we solve this different problem, and then we have to change our solution to the different problem back into a solution to the original problem. And in this case, we actually ended up with no solution, right? Because at the end of the day, we needed to take the square root of a negative number, which, for the purposes of this class, is not allowed. So those were quadratic in form. There are a couple of those, I think, on your homework. Or there might be one on your homework that will help you to maybe become less allergic to that. Any questions on the types of equations that we talked about last time? All right. Crickets. That means move on, I guess. Yeah, I do, by the way. I always want to strongly encourage questions if you have them, just because I know that, okay, maybe when I was a student, I used to have questions, but I was always like, I don't want to ask that because I don't want to either embarrass myself or I don't want to hold up the class. First of all, in terms of embarrassing yourself, get over it. I promise you'll be so much better for getting over it. Second of all, holding up the class, I guarantee you if you have a question, at least like in between 3 and 40 other students in this class have the same exact question as you. So please do ask it. Okay, so that's on questions. All right, then I guess if there's none, then we'll move on to A.7. So in A.7, we're going to talk all about inequalities. Okay, so before we talked about how to balance equations where we have an equal sign in between two expressions. And now we're going to talk about how to balance inequalities where we're going to take that equal sign and switch it up. We're going to have maybe a greater than sign or a less than sign or a greater than or equal to sign. Okay, so a couple basic properties of inequalities that we're going to talk about first. I guess these are probably pretty basic. So let's talk about transitivity first. Okay, so if I have two things, I have three numbers, and A is less than B, and also B is smaller than C, then what kind of relationship can we deduce exists between A and C, do we think? Yeah, C should be larger than A because A is less than B and B is less than C, so therefore A is less than C. Okay, so that's pretty simple. So then let's do another thing. Also, we can add things to both sides and preserve the inequality. Okay, so if A is less than B, if I add C to both sides, this inequality is still true. Okay, this inequality is still true. All right, for any number that I add. And since C can be a real number, it could also be, for example, a negative number. So addition and subtraction both fall into this category, right? Because adding a negative number is exactly what subtraction is, right? Just like how division is fancy multiplication, subtraction is just fancy addition. All right, that's addition. And then multiplication. Okay, so multiplication is the only tricky one, in my opinion. So why is multiplication tricky? Well, multiplication is tricky because we can multiply by a number and preserve the inequality only if something is true about that number that we multiplied. Does anybody know what it is? What condition do we need to have on a number C such that if I multiply both sides by C, the inequality stays the same? C should be a positive number. Right? C should be a positive number. And then What do we do if c is a negative number? We just flip the sign, okay? So the sign was facing to the right, and then it's facing to the left if c is a negative number, okay? And then for division, it's the same thing, right? If we divide by a positive number, we keep it how it is. If we divide by a negative number, we switch the sign. That's because division is multiplication by the reciprocal, and something like -3 is dividing by -3 is the same as multiplying by -1/3, right? So it's the same as multiplying by a negative number. So that's why we should still flip if we divide by a negative number too. Okay, so these are the basic rules of inequalities that we're going to use throughout this section. So are these pretty much familiar to you, or is this more new? Pretty much familiar? Okay, cool. Well, if you have any questions, then make sure that you email me, and we can set up an appointment, or you can come to office hours next week. All right, so let's talk about how to solve and graph linear inequalities. Okay, so what do I mean by linear? By linear, I mean that the highest power of x is 1. Basically, the highest power of x is 1. If I had an x squared floating around, what would I call it? Not linear, but quadratic, right? That's what I call equations involving squares. Okay, but I don't have any squares, so this one's linear. So let's see how we solve it. Well, we solve it in the exact same way as we solve regular equations. The only difference is if we multiply or divide by a negative number, we are going to do what? Everyone together. Switch the sign. Okay, that was pretty good, I guess. All right, so what are we going to do for this one? Well, the first step, in my opinion, would be to multiply out this guy and get 2x minus 6. And then we wanted to combine like terms. So I'm going to subtract 2x from both sides. If I subtract something, should I flip the sign? No. So I get 5x minus 11 is less than -6. And then I'm going to add 11 to both sides. So this was a minus 2x on both sides. And then a plus 11 on both sides. And I'm going to get 5x is less than 5. Now what should I do? Divide by 5. Now, do I need to flip the sign if I divide both sides by 5? No, why not? Because 5 is a positive number. Oops, this should be a 1, right? Because 5 is a positive number, I keep the sign how it is when I do that division. So x should be less than 1. Okay, x should be less than 1. Okay, so two new things that we're going to talk about with the inequalities that we don't have with the equalities are the solution set and the graph of an inequality. So we already talked a little bit about the graphs of sets. So what we're going to do first is we're going to describe the solution set, and then we are going to graph that set on the number line, okay? So the solution set is going to be, let me maybe move this down a little bit so I have some more room. The solution set, let me describe what that's going to be. It's going to be the set. Remember, a set is a collection of numbers which can be plugged in for x and make the inequality true. And I'm going to express this set using interval notation. Or if need be, I will use unions and intersections to describe this solution set using interval notation. Okay, so I want to describe all of the numbers that I can plug in for x such that if I plug that number in, the inequality x is less than 1 will be true. Okay, so let's think of a couple examples. Could I plug in 3 for x? No, why not? Because 3 is not less than 1. That would make the inequality false. We want to make it true. How about 0? Could I plug in 0 for x? How about negative 1 million? Yes. And every number in between, right? Every negative number. Okay, so the way that I'm going to write this using interval notation is I'm going to go from negative infinity, and we always put a parenthesis when we use infinities, okay? And I'm going to put a comma, and then what's the biggest number that I can plug in?
0. Oh.
I can plug in a number bigger than 0, but can I actually plug in 1? No, because 1 is equal to 1, right? But 1 is going to be what I write here. And what am I going to do to explain that I can do every number up to but not including 1? I'm going to use a parenthesis. Yeah. Okay, great. So how do I graph a set like this on a number line? Well, I put 1 on here. And what kind of thing am I going to draw on 1? An empty circle, or if you want, you could do like a parenthesis like that. That's also fine. Or you could do it above if you want, something like that. Just as long as it's clear that it's not included. So I'm going to do it with an open circle, and then I'm going to graph to the left, right? Left, right, okay. Left, correct, is what I should say. All right. So these are all the numbers which I could plug in. I can pick any of the ones that I want. I could pick this one, or 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 this one, and I could plug it in, and the equation would be true. Or the inequality would be true. Okay, so I fully expect that the hardest part about these problems like this is going to be describing the solution set in terms of interval notation. So if that's something that you're not super comfortable with, you might need a little extra practice. Come to office hours, and we'll do some extra practice involving sets. All right, so let's break out into groups now and work on a problem with a partner. We want to write the solution set in interval notation, and graph this inequality. And if your group wants a little help, then just raise your hand and I'll come around, okay? No, we'll keep that little equal sign. Yeah. Okay, how are we doing? Do we need a little more time? Okay, no one's raising their hand, so let's talk about it together. What's the hardest part? Is it solving it, or solution set, or graphing? Or it's all super easy? It's all super easy. Yeah, that's the thing, is it always feels, I feel like suspicious when I do math and it feels too easy. I'm like, something's not right here. All right, well, let's try to do it together, and hopefully it goes well. Okay, so the first thing I'm going to do is, I don't know, to subtract 8 from both sides. So, I mean, you could do it two ways. You could subtract 2 from both sides and add 3x from both sides if you want, or you can subtract 8 from both sides, which is what I'm going to do. So subtract 8, subtract 8. The only reason I'm doing that is because then I get to demonstrate this awesome rule, which says that if I divide by both sides by -3, what am I going to do? Flip the sign. All right, did I do that right? X is larger than or equal to 2. All right, how about the solution set? What's it going to look like with interval notation? 2 with a closed bracket, and then up to what? Infinity, right? Any number up to infinity. And why do I always put a parentheses on infinity? The reason I put a parentheses on infinity is because there is no stopping point. If I were to put a bracket here, it would infer that there was like a point at which I would eventually end this interval. But there is no point at which I end the interval. It's just a kind of notation, or what's the word? I'm dancing around this word. Convention. It's just a convention that we write infinity to say basically that this set goes on and on forever. You know, in another world, maybe they decided that intervals which look like this mean it just goes on forever, or intervals which look like this mean they go on and on forever, whatever. But the one that we have in our world is like so, and that means it goes on and on forever and never ends. Okay, so x is larger than or equal to 2. Let's graph it. Here comes 2. Should I have a closed or an open dot? Closed dot, draw to the right, bam, we're done. All right, how are we feeling about linear inequalities? Let's have some thumbs. Thumbs straight up in the air if you feel great, and thumbs sideways if and thumbs down if you're about to cry. All right, I'm seeing mostly thumbs up, so I'm going to move on to compound inequalities and make it more complicated. Okay, so the big difference between the two types of compound inequalities is sometimes we have ors and sometimes we have ands. Okay, and what do or and typically correspond to when we're going to be talking about a set notation with intervals? Or goes with the union, right? And then and goes with the intersection, right? Okay, so let's see how that's going to work out with these two. Okay, so we want to solve basically both of these individually. So 2x plus 7, subtract 7 from both sides, divide by 2. I think I get x. Let's do it. 2x is less than or equal to -6. Divide both sides by 2. I get x. And I divided a negative number by another number. Should I switch the sign? No, why not? Because the number I'm dividing by is positive. So I get it like this, and then I have an or, and then for the other one, I'm just going to get 3x is less than, add 2 to both sides, 6, so x is less than 2. Okay. So an or here. So here's what I'm going to do to demonstrate this. I'm going to graph both of these inequalities with different colors. I'll do one with pink and one with purple. You got it. One with pink and one with purple. All right. So the one with pink, let's draw that one first. That one's going to be less than or equal to -3. So let's first put -3 and 2 on our number line. So the first inequality says x is less than or equal to -3. So we would put a dot here, and then it would go like so, right? And then for the purple one, what would we have? An open dot here, and it would go all the way to the left as well, right? Okay, so the solution set is going to be the union of the solution set of these two. Okay, so I know that the solution set here, so this solution set is negative infinity comma 3 with a bracket. And this solution set with the purple one is negative infinity comma 2 with a parentheses. Right? And if I take the union of these two, then I will get the solution set for my big thing, which is going to be negative infinity comma 3. Now if I do the union of this set with negative, sorry, this should be a negative 3, right? Negative 3. And then I'm going to union this with negative infinity comma 2 with a parentheses. So who can remind me what it means when I write something like this? If I do a union, I'm going to get a new set. What's the rule for building this new set?
Anything that's in either.
Yes, I'm going to include in my new bucket. So it's like I have two buckets, right? Bucket number 1 and bucket number 2. And I'm going to make a new bucket, bucket number 3. And what I'm going to pour into my new bucket is everything that was in both of those two buckets. There might be some repeats, right? But that's okay. I'm going to pour everything from both of them. So I'm going to combine these two sets in the normal, like, common parlance understanding of combine, right? So what am I going to get? Negative infinity comma 2, right? Kind of strange. I just get the set on the right. Why is that? That's because every number which is in the first set is already in the second set. Okay? So if I combine a set with something that was already inside it, I just haven't changed anything. Okay? All right. So that's how we take that union. Any questions on this example? All right, then let's move on to the next example, which is an AND problem. Now, AND, okay, AND goes with this guy, right? The reason that I like, or the way that I like to remember that AND goes with the intersection is because the intersection symbol kind of looks like an N. So you could write like A-N-D, like AND, okay? That's how I like to remember it anyways. Or you can think of it as like, I'm going to do this and that. I don't know. Whatever. However you want to think about it. All right, so let's solve these ones individually, and then we'll take the intersection of their solution set. So this one, 2x plus, oh, these are the same, right? Okay, these are exactly the same. So we know that the solution set for this one was negative infinity comma negative 3, right? With a bracket. And then this one was negative infinity comma 2 with the parentheses, right? Those were the solution sets. So now that I have an AND, okay, let's graph them again. Actually, I'll just copy these down. That would be cool. Copy, paste, bam. Saves us so much time. Okay, so now, if I'm going to combine these using an AND, then I need to take the intersection of these two things, which means I need to think about all of the numbers which are in both solution sets. The number needs to be included in this set and included in this set. So how is that going to affect our solution set in this case? What part is maybe going to be removed? Sorry? I'm going to remove between negative 3 and 2. Okay, the reason that I'm going to remove this from the new set is because these numbers, while they are in one of the two, they are not in both because they are not in this second set. Right? So I should not include them in the intersection because the intersection is a new bucket, and the only things I'm going to put into my new bucket are the things which I know are in both of the other two buckets. Right? That's how I'm going to make my new solution set. So in this case, the intersection is going to be everywhere where the lines overlap, okay? Everywhere where the lines overlap, which is going to be from negative infinity up to 3, including 3, sorry, negative 3, including negative 3, because negative 3 is included in this set, and negative 3 is included in this set. So we should also include it in the intersection of those two sets. Okay, how do we feel about that one? Pretty good. Any questions on this one? All right, doesn't seem like there are any questions. So, yeah, that's compound inequalities. Basically, it comes down to taking the union or the intersection of solution sets. Okay, so that's why on the first day of class, or the second day of class, we spent so much time talking about set notation and how to do unions and how to do intersections and intervals and all of that stuff, because when we're doing inequalities, we're going to use that notation, and later on when we're doing functions, we're going to use that notation all the time to talk about the domain and range. So that's the relevance of set notation. So if you're thinking, I'm kind of bad at that, but I'm just going to let it slide because probably after test 1 it won't be back. That's a bad strategy because it will be here for the whole semester. So if you want some extra practice with sets and set notation, come to office hours. All right. Let's talk about the test point method. Oh, test point method. Okay, so what is the test point method? The test point method is used basically when we have inequalities which are quadratic or higher. Okay, quadratic or higher. Okay, so the way we use the test point method is we're basically going to set this up as if we were solving a quadratic equation as opposed to a quadratic inequality, which means I'm going to move everything to one side first. Okay, so step 1, move to one side. Move to one side. Okay, so what do we get? X squared minus x, and then minus 6, right? Is larger than or equal to 0. Okay, then step 2 is going to be solve for x squared minus x minus 6 is equal to 0. Okay, then we'll go back once we want to look at the larger than or equal to sign. Okay, we're going to solve this first. So how would I solve this equation? Everyone should be pretty familiar with this so far. What do I do on the left side? Factor, or else use the quadratic formula if you don't want to factor. We get x minus 3, x plus 2 is equal to 0. If I multiply two things together and I get 0, then one of them must be 0. So therefore, x is equal to either 3 or x is equal to negative 2. Okay, so now here's what we're going to do. This is why it's called the test point method. We are going to draw a number line. Big sigh. I feel you.
It wasn't even that.
On the number line, so step 3 is on the number line, put both zeros. Okay, so those would be negative 2 and 3. Okay, and now comes the test point part of the test point method. So step 4 is pick a number from each subinterval divided by these numbers. So here is subinterval 1. Here is subinterval 2, and here is subinterval 3. Okay, so I need to pick a number from each of these 3 regions on the number line. So I like to pick nice whole numbers, and I like to keep them as small as possible. Because here's what we need to do. We need to pick a test point. So how about negative 3, and I always like to pick 0 when it's available, and maybe 4. Here's why I like to pick numbers which are whole numbers and relatively small in absolute value. What we're going to do with each of these numbers is plug in to our inequality here and see if it's true or not. So here's what it looks like. So next, step 5 is to plug into inequality. So if I plug in -3 into this inequality here, then I get -3 squared is 9, minus -3, which is a +3, and then -6 is larger than or equal to 0. And my goal is to figure out whether this is true or not. Okay? Whether this is true or not. Well, if I take 9 plus 3, that's 12, minus 6 is 6. Is 6 larger than or equal to 0?
Yeah.
Yes, so this is true. So I know that in this subinterval, the inequality is true. Now let's try 0. If I plug in 0, I get 0 squared minus 0 minus 6 is larger than or equal to 0. True or false? False, right? Because -6 is not larger than or equal to 0. So in this subinterval, the inequality is false. And how about the last one? If I do 16 minus 4 minus 6 is larger than or equal to 0, what do we think? True. Very good. I can't underline. There we go. So it goes true, false, true. Okay, so the number line in the end, I'm running out of colors here. Maybe I'll do blue. Okay, so what is the number line going to look like? Well, first of all, am I going to include 3 and -2? Who says no and why? Yes, but the question is, you're right. You're getting ahead of us, though. So the question is, if I plug in -2, will the inequality be true?
Yeah.
Yes, it will be, because -2 will make this side 0. And 0 is larger than or equal to 0, right? It's equal to 0. So larger than or equal to is okay. So in other words, what kind of thing am I going to put at -2? An open dot or a closed dot? A closed dot, because -2 does satisfy the inequality. And then I'm going to draw my things in terms of I'm not going to put any line where it says false, and I am going to put line where it says true. So I move to the right, and I move to the left, and I get a solution set. What is the solution set here? -infinity up to 2 and including 2. And also 3, sorry, -2. And then 3 up to infinity, right? And what goes in between? A comma, or we want to use our set notation here. I mean, comma would be like technically correct. But the better way to describe it is I want to talk about this as if it's a single set. So this set is made up of 2 sets. So you could say, yeah, these 2 sets make up the solution set. But if we're talking about the solution set and not the solution sets, we should refer to a single bucket, which we form by taking each of these 2 buckets and combining them, which means I need to have a union here. What would I get if I did an intersection between these 2 sets, by the way? Do they overlap at all? No. So the intersection would be exactly nothing, right? So it'd be the empty set if we did the intersection between those 2 sets. Okay, so we want union in this case. All right, any questions on this test point method? Yes.
Where did you get the -3 and the 4 on the number line?
The negative what, sorry?
In the pink on the top under true.
Okay. The question is, where did these numbers come from? -3 and 0 and 4. Okay, so the reason that I picked those numbers, I picked them essentially at random. But what I need those numbers to do is those numbers need to be either, the first one needs to be something less than -2. So that's why I picked -3, because -3 is a number which is less than -2, and it serves the purpose well in the sense that it's easy to plug -3 into my equation or my inequality to see if it's going to be true or not. So you could have picked numbers like -500, or if you wanted, but you'd then have to go ahead and square -500 and then add 500 and then subtract 6 and see if that's larger than or equal to 0. It's just annoying. So that's why I picked -3. It's a convenient number. The next number I picked was 0. What I need that number to do is it needs to be larger than -2 and smaller than 3. I picked 0 just because 0 is really easy to plug in. 4, again, it's a little bit bigger than 3. So that's where those numbers came from. I'm just checking each region because I know that at -2 and 3, these are the only places where the inequality is actually strictly equal to 0. And we haven't learned about continuity yet, but there is a notion that if I have a continuous function, I want to ask when is it positive and when is it negative. Well, it can only go from being positive to being negative if it passes through 0. So that's why I graph those particular points, and then I check, well, as long as I know where it's 0, then if I can check the sign of just any given point in this region, then I'll know what is the sign of that function in the entire subinterval, because I know that it cannot change sign until it passes back through a 0, basically. But that's getting ahead of ourselves a little bit. For now, what you need to know is just you plot these things, you pick test points, and you plug in, you graph or don't graph, depending on whether it's false or true. But that's a very good question about where those points come from and why we're doing this. Any other questions? Yeah.
Why do you pick or not and? I'm sorry, maybe I missed that.
Okay, why did I pick or and not and? Okay, so this is because if I want to describe the numbers which I could plug in to this inequality and get a true statement, I could plug in 3 or 4 or any number bigger than that, right? But I could also plug in -2 or something smaller than -2, right? So because I have this choice of two different options, I say I can do this or that, right? That's where I got or from. Okay, but also there's just no way to describe this solution set. Like if you look at the graph, okay, there is no way to describe this set using an intersection, because an intersection is going to necessarily be an and. It's going to be something more like this is what an intersection is going to look like. Does that help answer your question? It's a little bit vague of an answer, but we can talk about it more in office hours. Okay, I'm going to move on now to rational inequalities. Okay, so the only thing I have to be careful about with rational inequalities, so first of all, the way I'm going to solve this rational inequality is by using the test point method. Okay, I'm going to use the test point method. But there's one very, 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 very important thing that I need to state right off the bat, which is that I am absolutely not allowed to include one particular number in the solution set. Anybody know what it is? I can't include 1 in the solution set necessarily, because 1 would make this side not defined. It doesn't make sense if you say something undefined is larger than 3, because how can you even grasp something that is undefined, much less state that it is larger than or smaller than a number? It's like it doesn't even exist. So it's kind of confusing, so we just throw it out right away. So first of all, we are going to say x should definitely not be equal to 1, or any other number that would make the denominator 0. So I'm going to put 1 on here, and the very first thing I'm going to do is I'm going to put an open circle at 1. because I'm not going to include that in my solution set. Then from there, now that I've dealt with that, I'm going to go ahead and solve this by multiplying both sides by that denominator. Get rid of it. Is larger than or equal to 3 times x minus 1. And, well, maybe I should be careful with that, because there's a question mark, right, about whether that number is positive or negative, right? Okay, so let's think about that a little more carefully. If x is larger than 1, then the denominator will be a positive number, and we multiply both sides by a positive number. And then if x is less than 1, then we're going to get a different inequality. And I might be butchering this. We'll see. 3 times x minus 1. Okay. Well, let's just go through and see what we get. And then we'll adjudicate this later. I think it might be possible that we just need to do this one, but we'll see. All right, so let's go ahead and solve them. If I get 3x minus 1, that's the same as 3x minus 3. If I move everything over to one side, I get x squared minus 5x, right? X squared minus 5x, and then minus 12, right? Okay, x squared minus 5x minus 12. Okay, so what am I doing here? Can I factor this? 3 and 4, 2 and 6, 12 and 1. Might well be that I wrote this problem down wrong. Let's think about that for a second. Well, I
Take the 15 and 17, then the 12 would be 14, and then we could do negative 7 and positive 2.
Yeah. Why don't we do that? Yeah, let's go ahead and do that. Okay, so we'll make this a 17, and we'll make this one a 17, and therefore the 12, when we subtract 3 from 17, we get 14. And now we can factor this. All right, this problem's a mess. Sorry about that. So let's factor it as x minus 7, right, and x plus 2 is larger than or equal to 0. Okay, so now what am I going to do? Aha, now I remember why we don't need to worry about this other case. Okay. So the reason that we don't worry about whether the number that we're multiplying by is positive or negative is because ultimately what we're going to do is use the test point method. So since we're using the test point method, the only thing that we're going to need to figure out is where is the numerator 0, and then we're going to pick test points from each subinterval, and then we're going to plug them in and see what we get. So in that sense, we don't need to worry about any of this stuff. What we're actually going to do is we are going to multiply both sides by x minus 1 and solve not this inequality, but rather this equality. So this is why we don't care about the sign of that denominator. So we solve this equality, and then what do we get? Equals to 0. Okay, so therefore x is equal to negative 2, or x is equal to 7, right? Aha, now I understand why this problem was this way. Okay, I'm really sorry, everybody. I taught this completely wrong. Allow me to start over. Here's what we have. A rational expression which, like I said before, if it goes from being positive to being negative, it had to have passed through 0. So I want to understand all the places where this expression is going to be equal to 0, okay? No, I did do this right. Oh my God, I'm sorry. God, this problem is such a pain in the ass. Okay. I need to understand when this equality is going to happen. The equality is going to happen exactly when, if I multiply over this x minus 1, I get x squared minus 2x minus 17 is equal to 3x minus 3. Like I said before, we move everything over to one side. Minus 14 equals to 0. There should be a 5. We factor, as we factored before, x minus plus 2 and x minus 7. Okay. X minus 7. So therefore, x is equal to negative 2 and x is equal to 7. Okay, so these are the places where this expression is going to be equal to 3. Okay, so we put on our thing negative 2 and we put on our thing 7. And the only thing that we need to do now is pick a test point from each subinterval. So the only thing that's a little bit different about our subintervals for this inequality is we're going to have actually 4 subintervals, because we have the 2 points where we're going to achieve equality, and we also have the 1 point at which the rational expression is not defined. And typically we're going to see a sign change at that point in the rational expression. So we're going to have subinterval 1 and subinterval 2, and then we're going to have subinterval 3, and then we're going to have subinterval 4. And we need to pick a test point from each of these subintervals. So I'm going to choose negative 3, and then I am going to choose 0 for the second one, and then I'm going to choose 2 since it's the smallest nice number there, and then in the last one maybe 8. Okay, so we finally made it through this. Sorry that took so long. Okay, so we have all of these test points. So what are we going to do? We're going to plug them into the original rational expression and check whether or not we preserve this inequality. So let's try negative 3. If I plug in negative 3 in the top, I get negative 3 squared, which is 9, minus, or rather plus 6, and then minus 17. Okay, so we get 15 minus 17. Is it larger than or equal to 0? No.
So we only plug it into the top?
To this guy, is that what you're talking about?
Yes.
I'm sorry, no, we need to plug in the denominator too. God, I got so frazzled here. But, of course, if we plug in the denominator, right, what do we get? Negative 3 minus 1. Okay, so in the end, we get a negative number on the top, which is negative 2 divided by negative 4, which is 1/2, which is larger than or equal to 0. Jesus, I am just messing this all up.
Wait, so why isn't it, why isn't it, greater than or equal to 3?
Oh my God. No, you're completely right. We need to check whether it's larger than or equal to 3. So I was right the first time that it's false. Okay. Hopefully we can get through the rest of this with no further mistakes. So that's one test point. So we are not going to graph in this region. Okay, we are not going to graph in subregion 1. How about if I plug in 0? Then in the top I get negative 17, and in the bottom I get negative 1, and the goal is to check whether this is larger than or equal to 3, which 17 is larger than or equal to 3, so this is a true region. So I am going to graph in between -2 and 1. How about between 1 and 7? Well, I picked 2. So let's plug in 2 into our inequality. We get 4 minus 17 divided by 2 minus 1 is 1. And our goal is to check if this is larger than or equal to 3. Well, 4 minus 4 is 0. So -17 is not larger than or equal to 3. So this would be a false. So we are not going to graph in this region. And lastly, we need to plug in the number 8. Okay, we need to plug in the number 8. So if I plug in 8, I get 64 minus 16 minus 17, all divided by 8 minus 1 is 7. Okay, so 64 minus 16 minus 17 is 31, right? So this is 31 divided by 7. Is it larger than or equal to 3? Yes, because 28 divided by 7 is 4. So 31 divided by 7 is bigger than 4. So 4 is bigger than 3. It's true in this region. So we are going to graph from 7 onwards. And now I think we're finally ready to describe the solution set of this rational inequality. It's going to be all of the numbers which are between -2 and 1. We are not going to include 1 because it is not defined for x equals 1. How about -2? Are we going to include -2 or exclude -2? We are going to include by virtue of the greater than or equal to sign. Okay? So we already determined that -2 is a number such that if I plug it in, I get equality. So -2 should be included because I'm okay with equality. Okay, and now comes a union, and the next set should be from 7 to infinity, and include, again, by virtue of this greater than or equal to sign. Okay, so we finally made it through that one. Again, I apologize for being helter-skelter there for a little bit. But yeah, rational inequalities, as you can tell, are a pain in the ass. It's really quite annoying. But what I do want to impress upon you is that this test point method is really powerful, and it's extremely useful. And can I have a show of hands of anyone who's going to take calculus next year, who's planning to take calculus next year? Okay, a lot of you, almost all of you, in fact. The test point method is going to come back in calculus in a big way. So scary. Yeah, so it's going to be used in calculus. I won't get into why, but it's a good thing to practice this test point method with inequalities now in this kind of safe environment before you move on to the big calculus class. All right. So we finally made it through. Dare I even ask, are there questions? Yeah, Ashley?
Hopefully this is an easy one.
Okay.
So in the first example of the test point method, we kind of plugged everything back into the simplified version of the inequality, but in this one we used the original.
Mm-hmm.
Is it just fine to use either?
It is fine to use either in this case because all that we did to simplify this one was subtract, right? And we know that subtraction is never going to change the sign. However, when we simplified this one, what did we do? We multiplied and then subtracted. So there's a possibility that in that simplification, we may have changed the sign. So the reason I went back to the very original inequality for the plugging was because this inequality with a greater than or equal to sign is not necessarily equivalent to the original. That's why originally when I was writing, we need to consider, well, did we multiply by a positive or a negative number? And there's two cases. So that would have been another way to go, but I think it's a little more complicated. So Yeah, that is basically why I went back to this original equation instead of the other one. The reason I used this one instead of the original is because it's simpler, and I know for a fact that it is completely equivalent. That's a really good question. Any other questions on the rational one? Okay, doesn't seem like it, so we're going to move on and talk about inequalities with absolute value. Okay, so one thing that maybe I will recall for us before we start this, is that the distance between 2 points on a number line is equal to the absolute value of their difference, which is also equal to the absolute value of their difference if I do it in the other order, by the way. So this was what we called distance, okay? So on the number line, what I meant by distance was like, how far would I need to walk to get from one point to another? Or how far would I need to walk in the other direction? It's the same, right? Because moving left and moving right, distance is always positive, right? So when we have an absolute value incorporated into an inequality, you can think of this as saying the following. This describes the distance between x and the number 7. This is distance between x and 7. And if we say should be larger than 2, then we can think about it in the following way. Here's 7 on my number line, and I want to include all the numbers x which are more than 2 away from 7. So that would be, here's 9 and here's 5. We'd put an open dot on both and graph in either direction. Why? Because this is explaining that we have to have a distance between x and 7 needs to be larger than 2. Okay, so that's the intuitive understanding of how we're going to do these. But the more mathematical approach is to consider the following. Consider the following. We need to understand the absolute value function. Now, the absolute value function does one of two things. If the number inside is positive, then the absolute value sign does absolutely nothing. The second case is if the number inside is negative, in which case, what does the absolute value sign do to our number? It changes its sign, which can be done to any number by multiplying by -1. Okay, so we're going to do the cases. Case 1, x minus 7 is larger than 0, in which case we just drop the absolute value and solve x minus 7 is larger than 2. We add 7 to both sides and get x is larger than 9. Case 2 is where x minus 7 is less than 0, in which case what does the absolute value sign do? It negates what is inside. So we end up with not x minus 7, but 7 minus x. And we keep larger than or equal to 0, or larger than 0. Not 0. Jesus. It should be 2. And so now what do? We subtract 7 from both sides. We get negative x is larger than -5. And then we divide both sides by -1. Since I divide by a negative, I flip the sign. So one of these two things is going to happen. Either it's a positive number, in which case we leave it as is, or it's a negative number, in which case we have to multiply by -1. Okay, so this is how we get the solution set, which is going to be, of course, any number which is larger than 9 or less than 5. So in this case, we get an OR situation, which gives us what? We get the interval notation -∞, comma 5. Should I have a parentheses or a bracket on 5? parentheses. Why? Because less than or greater than, not equal to. Okay, now a union, and then 9 to infinity. Okay, so this is how we deal with inequalities with absolute value. We need to ask ourselves, is the number inside positive or negative? Because depending on whether it's positive or negative, we're going to get two different results. Okay, so that's how we do this one. Okay, so next up we have this one, which says, roughly speaking, distance between x and 7, or from x to 7, is less than or equal to 2. So on a number line, what would that look like? We'd have 7, and then we'd go out to 9 with a closed dot, and 5 with a closed dot, and then we'd graph everything in between, right? Because those are all the numbers x whose distance is less than 2 away from 7, or equal to 2 away from 7. So that's, loosely speaking, what we're doing. But again, we can solve it by going through the cases. So case 1, x minus 7 is larger than 0, in which case we get x minus 7 less than or equal to 2. 2, because the absolute value sign does nothing if the number inside is positive. Then we add 7 to both sides. We get x is less than or equal to 9. Case 2, we get case 2, we are going to get x minus 7 is less than 0, in which case the absolute value sign flips it to a 7 minus x is less than or equal to 2. And then we move 7 over, we get negative x less than or equal to negative 5, divide by negative 1, x is less than or equal to 5. Sorry, larger than or equal to 5, because we flip the sign. All right. So these are how we solve inequalities involving absolute value signs. So the thing that we need to take into account with the absolute value sign is whether or not the number inside is positive or negative, which is why we get two different cases. So in this case, what is my solution set going to be? What is my solution set going to be? It's going to be from 5 to 9. Okay? If you ever get a little bit stuck on an inequality problem, you can always return to the friendly or not so friendly test point method. Okay? So one way you can do the test point method is find the numbers that will make the equality true, draw them on a number line, you'll get 5 and 9, and then pick a number from each subinterval, here, here, and here, and plug in and see if the inequality is true or not. So if you get stuck and you forget how to do an inequality with absolute values, you can always go back to the test point method. Any questions on inequalities with absolute value? Okay, well that's all that I have for this section, so I'm not going to start chapter 1, but really quickly before you pack up, let me tell you where we're going. I said really quickly before you pack up, let me tell you where we're going. Okay, so we've finished the review. So everything up until now is taught in detail in 111, which is the prerequisite for this course. So what I need you all to do is that if you are struggling a lot with the review part, is please come to my office hours and talk with me so we can make sure that we keep you on track for the course. Because one of the things about this course is it builds on top of itself, which makes it really hard when you don't understand what's going on in like a given week it makes it almost impossible to understand what's going on in the next week, and then it just snowballs from there. So it's really important, if you have a misunderstanding or if you're a little confused, to get help like immediately so that it doesn't have that snowballing effect. So next week we're going to talk about basically functions. So we're going to bring in a second dimension. So far we've been in one dimension, now we're going to be in 2 dimensions, and we're going to talk about all sorts of different functions and graphing and circles and all sorts of different things, but we'll wait to start that next time. All right, have a great weekend.